Hello friend, in this video lecture we want to discuss number system. Then the agenda of this video lecture is what is the number system, what are the common number systems, and then the interconversion of the number system. Let us consider what is number system. The number system is basically needed for counting the various items. For example, now in this picture here we see the star. We count them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decimal number system. Now we can define the number system as an order of set of symbols known as digits, which perform the arithmetic calculations with a well-defined rules here. Now what are the different common number systems here? The decimal number system, binary number system, octal number system, hexadecimal number system. Then this common number system, they can be classified on the basis of their bases. Then what is base here? The base is defined as the unique digit or symbol in the given number system. For example, if you take the decimal number system, it has a base of 10. So it consists of the 10 digits, that is 0 to 9. Similarly, if you consider the binary has a base 2. So it has only 2 bits, 2 digits 0 and 1. So these 2 digits we call as a binary digit. In short, it is called as bits. Then octal, there is having the base 8 here. So it consists of 0 to 7 digit. Then the hexadecimal having the base 16. It has a 0 to 9 digit as well as A, B, C, D, E, F alphabets. So A corresponding to 10, B corresponding to 11, C corresponding to 12, D corresponding to 13, E corresponding to 14, and F corresponding to 15. So there is another characteristic of the number system, which is called a positional weight here. So if we consider the decimal number system, which having the base 10, so therefore their weights are given at the power of 10. Similarly, for the binary, the weights are given the power of 2. Octal and the base is 8, so therefore the positional weight is at the power of 8, and the hexadecimal having the power of 16. Now we consider the interconversion of the number system. So we have the 4 number system which are commonly used, that is decimal, binary, octal, and hexadecimal. So we convert the decimal to binary as well as binary to decimal, decimal to hexadecimal, decimal to octal, and octal to decimal, as well as binary to octal, octal to binary, binary to hexadecimal, and the lastly that is hexadecimal to octal or octal to hexadecimal. Now let us consider the first, that is the decimal to binary conversion. Now we can have the simple number, we consider that is 26.75 to the base 10. Then what is to the base 2? Now this consists of what? The 26 as an integer part and the 0.75 as a fractional part. Now we want to convert the integer part into the binary conversion. So it has some rules here. So we can divide the decimal integer by 2 and consider the remainders here. We record every time the remainder till the quotient becomes 0. Now we collect all this remainder in the reverse order, that is from bottom to top. For example, we take this 26 as an integer number and we convert into the binary. So we divide this 26 by 2 and write down the quotient and the remainder here. So if we divide 26 by 2, the quotient is 13, the remainder is 0 here. Similarly, we take this quotient and we divide by 2, then it has a quotient of 6 and the remainder is 1. So in this way we continue this process till the quotient becomes 0. Now we collect all this remainder in reverse order, that is from bottom to top. Therefore the 26 to the base 10 is equal to 1, 1, 0, 1, 0. So the last one is called as MSB and the first one is called as what? LSB. That is the least significant bit and the most significant bit. Then we consider the fractional part. We multiply the fractional part successively by 2 and record every time the integer here. So we carry out this process till the product becomes fractional part becomes 0, or we can continue it for 3 or 4 times. That depends upon your accuracy here. Then we connect the results in a forward order of the integer here. For example, 0.75. Then you multiply 0.75 by 2, then the product becomes 1.50. The integer is 1. Similarly, you take this 0.5 and multiply it by 2, then it becomes 1.00. Then what? The integer is 1. So now here the fractional part is 0, 0, or therefore we will not continue this process. Then we write down this integer as a 1, 1. So therefore 0.75 to the base 10 is equal to 0.11 to the base 2. Now similarly we consider the binary to decimal conversion here. Now the procedure is very simple here. Then we write down the binary number, then we write down the weight of the each binary number to that particular position, then cross out the weights corresponding to the 0 bit and write the uncrossed weight to get the equivalent decimal number. For example, we consider this number 10111.1102 and convert it to the decimal equivalent here. The solution is that we can write down the given binary number, then write down the weight corresponding to each binary digit, that is bit. So if you consider this binary point, to the right side of the binary point the weight is 2 raised to minus 1, minus 2, minus 3 like this, and on the left side is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4 and 2 raised to 5 like this here. Then we can cross the weight corresponding to 0 bit. So therefore we cross 16 as well as 1 by 8. Then finally we can add all these bits to get the equivalent decimal number. So therefore this binary number 10111.1101 corresponding to 47.8.25. Now consider the octal to binary conversion here. Again it has two parts. One is the integer part, other is the fractional part. The procedure is same as the decimal to binary conversion, except that here the base is 8. Therefore we divide by 8 here and write down the remainder in the same order here. So for example we consider the 5 to 6 to the base 10 is equal to 8 here, or to the base, what is to the base 8 here. Then we divide this 5 to 6 by 8 and write down the quotient, that is 65, and the remainder is 6 here. Then divide 65 by 8 and write down the remainder here. So this process continues till the quotient becomes 0. Then we collect all this remainder in a reverse order, that is from bottom to top here. Hence 5265 to the base 10 correspond to 1016 to the base 8 here. Now consider the fractional part. Again the procedure is same here, which is used in binary to decimal to binary. Here only we multiplied by 8, because since the base is 8 here, and record the integer in a forward order. So, for example, you consider 0.15 to the base 10 is equal to what is to the base 8 here. We multiply 0.15 by 8 and write down the product, that is 1.20, and then integer part is 1 here. Then we take this fractional part 20 and multiply by 8, so we can get 1.60 to the base, then integer part is 1. So this process I will continue it for 4 times, and then finally we connect all these integer in a forward direction. So therefore 0.15 corresponding to 0.1146 to the base 8 here. Now octal to decimal conversion here. Then here we can write down the octal number, then write down the corresponding weights to its position, then multiply all weights to their corresponding octal digit, and finally add all the products to get the equivalent decimal. For example, you consider the octal number 147.43 and convert into the decimal here. So simple method is write down the octal number, that is 147.43. Then their corresponding weight sheets 8 raised to 0 from if you take the from decimal point octal point, 8 raised to 0, 8 raised to 1, 8 raised to 2, and on the right side 8 raised to minus 1, minus 2 like this here. Then we multiply by each bit digit by its weight here, and we can get the corresponding decimal number. So this is the procedure here. Now we consider binary to octal conversion here. So in this binary to octal conversion, so we can form the group of the 3 bits here. Why we form the group of 3 bits here? Because the maximum octal number is 7 here. So convert 7 into the binary, so it corresponds to 111. That is, it requires the 3 bits. So therefore we can form the group of 3 bits here. So then we consider for example, you consider this number here 1100.1111 and convert into the octal number. So simply we write this octal number, then we form the group of 3 bits here, that is we take from our binary point and go to the either right side or left side here. We go toward the right side here, then we take 0, 0, 1, then 1, then there is no bit, so we put the 0, 0 here. And on the left side here, again we start from this binary point, we have the group of 3 bits 1, 1, 1, then 1, 0, 0, and 1 is remaining, then we put the 2 zeros here. Then we convert this binary into the corresponding digits here. So therefore 001 corresponding to 1, 100 corresponding to 4, 111 corresponding to 7, as it is given in the what about table here. So therefore the octal number 147.14 you can get here. So this is again octal to binary conversion. The process is again same here. We can write down the octal number. Then we form the group corresponding to each digit. We can write the group of what 3 bits here. 4, for example, 4 100, 5 101, 6 110. Then it's a point. Then 2 corresponding to 0 1 0 like this here. So hence this is the equivalent binary number. Okay. Then we consider the decimal to the hexadecimal. So the base of the hexadecimal number system is 16 here. So therefore we divide this what integer decimal number by 16, and again we can record the what remainders here and connect them in a reverse order. For example, we take the number 5432 to the base 10. Then what is to the base 16 here? Then we divide this 5432 by 16. Then write down the quotient as a 339. The remainder is 8. Then you take this quotient as 339 divided by 16. The remainder is 21. Quotient is 21 and the remainder is 3. So this process is continuous till the quotient becomes 0. Then finally we can collect this remainder from bottom to top. That is in the reverse order here. So therefore 5432 to the base 10 corresponding to 1538 to the base 16 here. Then we consider the another part, that is the fractional part. In the fractional part we can multiply by 16 here and write down the integer here. So for example, if we take 5452 to the base 10 is equal to what is to the base 16. Then you multiply 0.52 by 16, then the product is 8.32, integer is in this case 80. Then you take the fractional part 0.32 multiplied by 16, then we can get 5.12, the integer part is 5. This process continue either up to 3 times, 4 times, that depends upon your accuracy. So if you see the last here, we can get the integer is 14, but there is no 14 digit here, the 14 corresponding to E here. So therefore this 0.52 to the base 10 is equal to 0.851 E to the base 16 here. Then similarly we can consider the hexadecimal to the decimal conversion. Here is the same procedure here. Then we write down the what octal hexadecimal number as a BF3.42. Then we write down the corresponding weights corresponding to each digit here. For example, 3 having the weight of 16 raised to 0, F having the weight of 16 raised to 1, and B having the weight of 16 raised to 2. Similarly, 4 having the weight of 16 raised to minus 1, 3 having the weight of minus 16 raised to minus 2. Then we multiply each digit by its weight here. The B the corresponding to 11, therefore 11 multiplied by 16 raised to 2. Then F corresponding to 15, 15 multiplied by 16 raised to 1. Then 3 corresponding to 16 raised to 0, therefore 3 multiplied by 16 raised to 0, and so on. So therefore then we add all these weights here to get the corresponding decimal number as a 3059 to the 0.2617 to the base 10 here. Then we consider the binary to hexadecimal conversion. Again here the hexadecimal number is maximum is F here, that is corresponding to 15, and here see conversion in the binary is 4 1, that is 1 1 1 1. Hence we can form the group of the 4 bits here. For example, if you consider the number here that is 1100111.0011 and convert into the hexadecimal here. So we can write down the given hexadecimal number. Then write down the form the group of the 4 bits starting from this point here, that is 1010, then 1011, then 11, then we can put the 2 zeros here, so it doesn't change the number here. Similarly from this point here, that is 0011, then single 1 is remaining, we put the 3 zeros here. Hence the corresponding then convert each this group of 4 bit into the corresponding hexadecimal number, that is 001 corresponding to 3, 1011 corresponding to B, 1010 corresponding to A, 0011 corresponding to 3, and 1000 corresponding to 8 here. Hence the equivalent hexadecimal number is 3BA.38. Then similarly hexadecimal to the binary conversion. Again we can form the same group of the 4 bits here, binary bit. So we take the number as BA.F4. So B means the 11 here, so that is 1011. A means 10, that is 1 0, B means 1 0 1 1, A corresponding to 1 0 1 0, and F corresponding to 1 1 1 1.